Hello everybody, today our lecture will concern the macromolecular dimensions. If I consider a polymer, this polymer is composed of n repetitive units. And as I mentioned before, by varying the number of repetitive units, the chain length of the polymer and thus its molecular weight will vary. As Tg is mass dependent, so also it will follow, and so that the rigidity and the flexibility as Young modulus will be changed. Thus the polymer chain length affects the polymer applications and processing. For example, if we consider the polyethylene, for low molecular weight or for low number of repetitive chains, can be used as gloves, for example. By increasing the number of repetitive units, we can get higher mass and we can use it, for example, as garbage box, etc., etc. So we can conclude here that the chain length is an important another parameter that we should use to compare different kinds of polymers and also to determine their macroscopic behavior. So how to define the polymer mass? If I consider a polymer sample, in this polymer we can find the polymer chain having 5 repetitive units. So I will define I as the number of repetitive units of the monomer in the polymer chain. This chain having 5 repetitive units has specific mass. I will also name it M5 according to Mi, where Mi is the mass of polymer chains having I repetitive units. In plus to M5 and chain of 5 repetitive units, we can find chains with 10 repetitive units having M10 as mass, 15 repetitive units having M15 as repetitive units, etc., as mass, etc. So in the polymer, I can't find just one chain having 5 repetitive units. I can have many chains having 5 repetitive units. So I have to quantify the number of chains having 5 repetitive units. And here I will give them the number N5, where N is the number of polymer chains having I repetitive units and thus having M5 or Mi mass. So we can find the sample or our polymer sample, a distribution of number of molecules or number of chains according to their mass. The total number of polymer chains in the whole sample is N, where N is the sum of all numbers of chains of each I repetitive units. So if I consider the example of chain of polymer sample having M5, M10 and M15, here we can take the example of 8 chains having 5 repetitive units, 7 chains having 10 repetitive units, and 5 chains having 15 repetitive units. So the whole number or the total number of chains in this sample are N5, N10, and 15, and here are N it's equal to 20. Also, it's important not just to quantify the number of chains having specific repetitive unit and to determine the total number of chains, but it's also important to determine the fraction of each kind of chains in the whole system. So here I have to define the fraction of xi, which is the fraction of number of polymer chains of mass mi. So if I want to calculate this xi, it's the number of chains having I repetitive units over the whole number or the total number of chains in the system. So xi would be defined as an I over n, or we put n on its value, so we have an I over the sum of total an I in the system. Here, if we calculate xi for our example, we will find for each group of chains, it's a fraction in the total number of chains in the polymer sample. Here, as xi, it's a fraction, so the sum of all xi in the system should equal to 1. Parallel to the number of chains having specific repetitive units, each group of chains has a mass. So if I consider, for example, our previous example, where we have M5, M10, and 15 repetitive units, so the mass of the chain, of the group of chains having 5 repetitive units is equal to the number of these chains times the mass of the polymer chain having this 5 repetitive unit. So I can define the mass of each group of chains as the number of these chains times the mass of each polymer chain. So here, for example, if I consider the M10 and 15, I can calculate the weight of each group by having the mass of each kind of chains. So here, for examples, for the N5, we have for the I repetitive units, we have, for example, 8 chains, and the mass of each chain, for example, here for the M5, it's 500 grams per mole. So I can calculate W5, which is equal to M times 500. And so that for the other groups. The whole mass or the total mass of the all chains in the system will be defined as W, where W is equal the sum of all masses of all groups, and as Wi is equal to an IMI, so I can put it as the sum of an IMI. So here in our example, W is equal to N5 M5 plus N10 M10 plus N15 M15, and it's equal to 86,000 grams per mole. Also, it's important to know the fraction or the mass fraction of each polymer group in the whole system, so that I can define Ci, where Ci is the fraction of weight of polymer chains of mass Mi, and it's given by the formula Wi, which is the mass of the group I, over the whole or the total mass or the total weight of all chain groups in the system. So Ci equal Wi over W. Here in our sample, we can calculate Ci and we can find its value for each group of chains. And as I said, for the Xi as its fraction, the sum of all these Ci or all these fractions should equal to 1. As in the polymer sample, we can find a certain high number of molecules, so it's impossible to have exactly the same length for each molecule or for each chain. So here we can talk only about a quantity in an average way. Okay, so how we can deal with a parameter that can help us to quantify the molecular weight of polymers in average weight. So we'll have two kinds of average molecular weights. Here we have the number average molecular weight. So if I want to define or calculate the number average molecular weight, first it's given as Mn, average number molecular weight of polymer chains. It should be equal to the mass of each kind of repetitive units times, as it's as number, times the fraction of each number of chain groups in the system. So I can define the number average molecular weight as the sum of the fraction of each chain groups times the mass of repetitive units, specific repetitive units of each group. As xi it's equal to an I over the sum of an I or over n, so that the number average molecular weight it's equal to summation of an IMI divided by the summation of an I, so it's equal to an IMI summation of an IMI over whole n. So this Mn is the total weight of all polymer molecules in a sample divided by the total number of polymer molecules, as it's equal to the total weight of all polymer molecules or of all polymer chains. Instead of summation of an IMI, I can put W, which is the total weight of all polymer molecules in a sample. And plus to this number average molecular weight, we can define weight average molecular weight, which is MW. It's weight average molecular weight of polymer chains. So for each M with specific repetitive unit, as I said before, we have fraction in mass. As we have fraction in number, we have here fraction in mass. So to determine the weight average molecular weight, I have to multiply the fraction of weight of each I times the mass of each I. So here the whole or the weight average molecular weight equal the sum of all Ci Mi. And as the fraction Ci is given before as Wy over W, I can combine these two formula and I can develop Mw as the summation of Wi Mi over W. And if I put Wi by its value as an IMI, the weight average molecular weight will be a summation of an IMI square over the summation of an IMI. In the Mn or the number average molecular weight formula, we get an IMI or the summation of an I. Here I find that I added one Mi up and one Mi down, and as I have more Mi in the formula or highest value of Mi, so Mw is higher in value than Mn. So I can here to be able to help you to remember this formula, I will give you the specific trick بدكم طريقة لتحفظوها. If I have X average Y, I can define X average Y as the sum of X of each Y times Yi times divided by the total X. So if I consider the number average molecular weight, where the X is the number and y is the molecular weight. So mn, number average molecular weight, equal sum of number of each y times y اللي هي molecular weight divided by the total x. Here it's the total n. So if I replace summation of ni over n by its value xi, I will get back the formula mn that I used in the 2 slides before. Same for mw, weight, average molecular weight, so it's equal to the weight, which is x, times y divided by the whole x, which is a whole weight. And if also I replace ci by its value wi over w, I will get back the formula of mw, which is equal to the summation of ci mi. After studying and developing this formula, I need that you determine as homework relation between xi and ci as general formula, and also to determine relation between the average molecular weights in number and in weight as function of xi and mi. In plus to average molecular weights, to characterize polymer sample, and as we have a variety of chains, so we should determine the dispersity of this sample. So here I will define the dispersity index, which is a parameter that measures the distribution of molecular mass in a given polymer sample. So D, or sometimes we'll find that polydispersity index, it's presented as PDI, but the new naming of this dispersity, it's D. So D, it's equal to MW over MN. So as MW is higher than MN, as I mentioned before, so dispersity is always higher than 1. The typical values for the dispersity is between 1.5 and 2. And usually using this D, we can say if the system is monodisperse or polydisperse. So if according to the broadness of the peak of the variation of the fractions in function of mass in a polymer sample, we can quantify the dispersity in the system. So we can say here that as its sharp peak we have monodispersed system almost, and it's as it's broad we have polydispersed system. This point, it's very important for the application of polymers, because we should have usually typical values between 1.5 and 2, because as you know, the mass influences the Tg, and if I have large variety of masses in the sample for the application, I can't control the Tg of the system. So for best applications of a sample, a polymer sample, we should have monodispersed system. Also, to determine the number of repetitive units, I, we can divide the mass I of the chain having I repetitive unit by the molar mass of the monomer, and we can get the number of repetitive unit in a specific polymer chain. In parallel, we can determine the degree of polymerization, which is average number of monomer units by polymer chain. As is a average number, so it's equal to Mn, which is number average molecular weight divided by molar mass of one monomer unit. So here, in these macromolecular dimensions, we are able to determine the number of polymer chains, the weight of these polymer chains, and the fractions in number and in weight. We are able also to determine the average molecular weights in number and in weight, and also we are able to determine the dispersity and the degree of polymerization. Hereafter, I will give you an example, calculation example. If we consider a theoretical polymer sample composed of two families of monodispersed compound, respectively of number of chains for the first group, we have 8 chains of M1 1000 gram per mole, or for the second family we have 2 chains of 100,000 grams per mole. I need here that you calculate the fraction in number, in weight for each family, and the average molecular weights in number and in weight, and also the dispersity of the system. I will give after here the solution, but I propose to you to stop the video here to make the calculation and then to verify the solution in the slide after. So here, if I consider the first family, I said I have 80 chains, of each chain have mass of 1000 gram per mole, and for the second family I have 2 chains where I have for each chain a mass of 1000 grams per mole. So if I want to calculate the fraction of the first fraction in number for the first family, I have here the first number of chains is equal to 8, here I have equal 2, so the total number of chains is equal to 10. The fraction of the family 1 is 8 over 10, so 0.8. And the fraction of the second family is 2 over 10, so it's equal to 0.2. 0.2 plus 0.8, it's equal to 1. If I want to calculate the fraction of in weight, as the formula, it's an IMI divided by the summation of an IMI. So here I want to calculate the summation of an IMI, which is equal N1 of the first family times M1 plus N2 of the second family times the mass of each chain of the second family. So I will get the value of the summation of an IMI. Here now I can calculate the fraction of weight of the family 1 by dividing N1 M1 divided by the summation of an IMI, and same for the second family. The summation of CI C2 should equal to 1. Now to calculate the average molecular weights in number and in weight, I have to apply the formulas. I put the values, each values here, and I will get both Mn and Mw. By applying the formula of dispersity, we will able to calculate the dispersity of our sample, and here we will find the D, it's very high. It's 462, it's much higher than 1, so we do have here polydispersed system, and we can conclude here as we have x1 is equal to 0.8, so almost 80% of chains do not represent more than 3.8% of the total weight of the sample. To practice, I will give you here an exercise. If we consider the following polymer sample, I gave you here the I and the MI, and I need that you calculate XI, CI, average molecular weights in number and in weight, and the dispersity. See you next time.